I'm still waiting for the other participants to join, so just bear with me for another maybe 1 minute.
Hi, Albert.
Hi.
Cyril. Two of us. Okay, that's a good start.
Yep, just to us at the moment, so
There'll be a few more come along, I think.
I hope so.
Have you had a good week, Albert?
Not bad. It's just like these days is like every day, isn't it?
It is, yeah. I went for a walk yesterday. I normally go every morning, but the last few mornings I piked out because of the temperature and that, so I didn't. Normally I just get myself and go pretty well first up in the morning.
Good.
Today I went out and did a bit of gardening. It's lovely being out in the sun there for a while.
Yeah, today's weather is much better than last 2 days.
Yeah.
Yeah, it was cold, but now, anyway.
Yeah, I was trying to ring you over the holiday break, but I didn't have your phone number. I sent you an email at the end of last term, but I had to send it to U3A. I don't know whether you got it or not. I was just thanking you for what you've done in the big history in the China there over the longer time. And then I thought, oh, look, I don't know whether you got it. I'll try and ring you. And I looked up in the phone book and I found an Albert Yip in Box Hill.
No, I'm not in Box Hill. there are quite a number of Albert Yip.
Yeah.
I personally know another one who is a medical doctor at USD Melbourne.
Oh, yes.
He's also a lecturer. I think he's a lecturer or something at USD Melbourne.
Yes. And I think the other address was up in Doncaster or somewhere, and I thought that sounds too far away. And the fact you do another one down at Box Hill, I thought, well, maybe you're going to be living down that way.
The other LBU I know, actually, we published papers on similar lines.
Yeah.
When I was still being academic, so I was writing about online learning, interactive learning, and so forth. It seems he is also in the same thing, but obviously he is more focused onto medicine, whereas I'm more focused on a more general aspect of online learning.
Yes.
But anyway, I'm live on YouTube as well. So.
Oh, are you? Oh, well.
Maybe let's get started.
All right, because we both go on YouTube when that's happened, do we?
Yeah, you can. Yeah, because because on YouTube they can actually streaming to more people. Let me see on YouTube. On the other side, I have at the moment no other concurrent user at the moment, but it doesn't matter.
No.
Let's get started. Yeah.
When your participants talk to you like now and you're on YouTube, we project onto YouTube as well, do we?
Yes.
Yeah, okay.
Yeah.
Yes.
Yeah. You are live on YouTube at the moment.
Right.
But unfortunately I only see your top part of the screen because I think I got the resolution wrong.
Oh, okay.
But anyway, let's get started. So I will switch over to share screen.
Yes.
Share screen. Hopefully we'll see the screen. And I will let the people in YouTube also see the same screen. Okay. This is the number 11. We are looking at the formation of our solar system. So basically, about 4.65 billion years ago, somewhere in our neighborhood, there was a supernova explosion. This supernova explosion caused some of the gases nearby to starting to collapse, and then eventually form our total solar system, and then eventually gradually graduated into the form we see today. So this is a general process. The reason why we know that there is a supernova nearby is because we found all the minerals that is created during supernova on Earth. Otherwise, we don't know it is due to a supernova. But because it is a collapse of a large gas of hydrogen helium, so we would expect in our solar system, we have mostly hydrogen, etc. So let's look at how it is. So around 4.6 billion years ago, with the gravitational collapse of we say it's a small part of a giant molecular cloud, but that small part is very large actually to human standard. Now most of the collapsing mass actually is collected in our sun. So the sun represents almost all the mass of the whole solar system. The rest has been flattened into a disk. The reason why it is flattened into a disk is all about the physics angular momentum. So you have some other masses moving towards a common center. They often is not balanced. As they are not balanced, therefore they will start rotating. And that rotation will cause all the other things to clump into one disk. So this is the so-called Nebular hypothesis. Starting from somewhere there was a star, the star must be very large, and therefore the life cycle is shorter, and somehow, somewhere it collapsed. It burned out its life and eventually becomes a supernova, and the supernova trigger the gas nearby, and then cause our solar system. So a giant molecular cloud about 20 pc. 1 pc is about 3.25 of light years, so it's pretty large. It's about 30 light years. The fragment in the cloud roughly 1 pc, so it's running roughly 3.25 of light years. Further collapse of the fragment lead to formation of the dense core at the center, and then this collapse, and then eventually becomes our star. So about 2% of the solar system is all these heavier elements. So about 98% is actual hydrogen and a little bit helium. So it is our solar system is a first generation star triggered by a collapsing star nearby. How do we know that? Okay, we look at all the materials that is around us, and then study them. So a meteorite is a solid piece of debris, and then that is fortunate enough or not fortunate enough to fall into the Earth's gravitational attraction field, and then eventually enter into the atmosphere. Most of them will be burned off, but some of them large enough will be able to survive, and then we can collect them and look at what they are. So that's one way to know about the makeup of our solar system. they are grouped into different geological names. So I'm not particularly familiar with all these geological names, but one of them is this chondrite, something like that. And in there, we look at what is inside. Now, most of them, because of their falling through the atmosphere, get burned up, and therefore they will melt. But sometimes in the middle, some part will not melt and keep its original state. So that is what we are trying to look at. So there are different kinds of these things. So they are grouped into two groups. One is called CM group and a CI group. I don't know how they group to each other, but you will notice that there's quite some water there. So although we are talking about we have a original hydrogen gas, but the supernova must have produced quite a bit of oxygen, and then the oxygen, when it being exploded into this cloud, so some of this oxygen will be able to react with the hydrogen to become water. So we have quite a bit of water in our solar system. The age is estimated by dating all these meteorites in order to find the oldest object. So that's how we know about the age of the solar system at the very beginning. I will come into these questions next time when we talk about Earth. We'll talk about our planet. Today we are mostly looking at the whole solar system. So we probably is a second generation first generation triggered by a second generation or a second generation. We probably don't know, but obviously nearby there must be some other star explosion in order to create all that material which is found on Earth. The sun, because of the angular momentum, the Nebular eventually turn around, and all the major attraction from gravity will be concentrated within the sun, our sun itself, but some of them will be spinning around in orbits around the sun. It takes about 100,000 years for all these gas to eventually drop together and then becomes sufficiently hot. When the temperature gets hotter and hotter, and eventually our sun will get ignited into what we see today. So it is very similar to one of those stars which have been studied quite extensively. To us, we are more interested is how the solar system. What is the solar system? Let's understand what is the solar system first, and then we'll concentrate on Earth, and then we'll look through the evolution that's happening on Earth. So at the moment, we're just looking at the formation of solar system, which probably take about 50 million years for the sun's core to be hot enough to start the fusion of hydrogen into helium. So it will mark the entry of the sun into its main sequence. So this is the life cycle of the sun, and we are somewhere in here now. So we are approximately 1/3 of its whole life. But to us, maximally we will be somewhere here. The Earth will exist somewhere here, and then our sun will grow into a red giant. And when the sun grows into a red giant, the whole Earth will be within the sun. The red giant is much larger than the current sun, and it will be more than the orbit of Earth, and that means at that time the Earth will disappear. So we probably, if there's any life on Earth, life probably will exist for another 4 billion years. After that, the sun will start to be too hot for Earth to sustain life, and eventually when the sun becomes a red giant, the whole Earth will be eaten up by the sun. And therefore, at that temperature, I don't think there is any possibility of life. So probably life will exist around here 1 billion years after the formation of our solar system up to now. So that is about 3 billion years of life. And then I think there will be another 2 to 3 billion years of life before Earth is eaten up by the sun. So we are somewhere in the middle of that life possibility. This the diagram at the top here represent the stars in their relative size. So the top diagram there is size-wise is correct, but distance-wise is not. The lower top here is the distance that is correct, but the size is not correct. So you only sun, if the sun is here at the top here, then this is Saturn, and that will be Venus, Jupiter. Sorry, Jupiter. That will be Saturn, and we are somewhere here, a tiny dots. And then these are the gas giants. So we will be looking at these 3 planets. There are 4 here, but we will not look at our Earth today. We will look at the other 3, and then we'll look at these 4. So look at what are their compositions and so forth to have a better understanding of the sun. This is the sun, so you will see the sun is much larger than any one of us. And in fact, Earth is not that big. Earth is quite small in that sense. Okay, how the planets are formed. As the proton systems start rotating, some of the debris might be moving a little bit faster than the other debris, and then they will chase up with some other thing and cause a collisions, and then will join together, becomes one piece. As they started moving around each other more and more, then their mutual gravitational attraction will attract them together, and eventually all collated into the planets. So that is what we believe how the planets was originally created, is through accretion. That means just like if we have some flour, as we add a little bit of water in the flour will initially lump together, and as you continue to add water, that water becomes similar to the gravitational force attracting all the small pieces together, and eventually would becomes a large piece. So something similar to that happens. Sometimes the debris does not actually totally collide with each other, and sometimes even if they have collide with each other, there will be fragments ejected outside, and that fragments can also accrete into a moon. So there are a number of moons near our planets. In particular, our moon collided with us at an angle, and therefore it shifted our rotational axis, and that give us the season on Earth. Okay, so let's look at the so-called inner solar system. The inner solar system consists of 4 planets. We are one of them. So there are other 3. We are the 3rd one from the sun. So the closest one would be Mercury, and then Venus, and then Earth, and then the next one out is Mars. So we call these 4 as the inner planets because they are separated by a asteroid belt, and the for us is quite different from the other planets outside of the asteroid belt. The reason is because these four, the Mercury, Venus, Earth, and Mars, are much heavier in terms of density than the rest, and therefore it has a larger gravitational force attraction towards the sun. Heavy objects tend to come to the center, and that's exactly why we have these four heavier planets near the sun. First of all, the Mercury. Mercury is about halfway, 0.4. So 1 AU is the radius of the Earth's orbit around the sun. So 0.4 is about half, 40%. It is closest to the sun of all the other planets. It is also the smallest in terms of mass. It is about 5% of the mass of Earth. So it's 5.5%. It's less than 6% of the mass of Earth. It has no natural satellites. It has no moon. Besides impact craters, which you can see on the photo, its only known geographic features are ridges. The atmosphere, we don't believe there is much atmosphere on Mercury because it's so close to the sun. The sun's solar wind will have blown off all the gas surrounding Mercury, and therefore Mercury shouldn't have any gas around it. It shouldn't have sufficient gravitational force to attract a permanent existence of gas around itself. So it shouldn't have a atmosphere. The same thing, it is the smallest and the innermost. It takes 87.97 days to go around the sun once. That means on Mercury, 1 year is 88 days on Earth. Because it's so close, so that is the quickest. There is something called resonance. That means the rotation of planets will affect each other. Mercury being the innermost, it is much more controlled by the sun rather than by other things. The rotation itself is quite unique because it is tidally locked to the sun, similar to how the moon is tidally locked to Earth. In that sense, that means the Mercury rotational axis will be something similar to the rotational axis of our moon. We always see the moon on the same side. We cannot see the other side of the moon because moon and Earth are tidally locked together. So is Mercury. Mercury has one side always facing the sun, and therefore that side will be very hot because it's always facing the sun. On the other hand, the other side will be less hot. But as the Mercury itself is actually rotating, although one side is always facing the sun, that means its summer is quite long and it's quite hot. The for Mercury is half 1 year. Sorry, 1 day is half a year. No, 1 day is 1 year. Is almost the same. Its own rotation is almost the same as rotation around the sun, and therefore, in 1 year, that means when Mercury moves around the sun in one complete circle, its own axis only rotate again 360 degrees. That means 1 day. So on Mercury, 1 day is equal to one year. And you can imagine in the middle of the day, you have been always facing the sun for the whole half a year. So it got very hot. So its temperature rate can range quite a bit depending on whether it's the daytime or the nighttime. On daytime, it can heat up to 400 something degrees C. At nighttime, it can drop to about negative 133 because it takes a long time. The day is very long, put it that way. The day is very long, the light is very long, and therefore when it's facing the sun, it got heat up until very hot, and eventually when it go to the becomes night, then it will cool, and then becomes very cold. The next one is Venus. Venus is the second brightest natural object in the sky besides the moon. And this is a calculation of the position of Venus over about half a year. We are at the moment, I think I have a look here. Yes, yesterday, May 4th, Venus will be its most northerly declination of this period. The next time it will appear like that will be 2077. So at the moment, it is very close to the horizon. It's only 4 degrees north of the horizon. It's very close on the horizon at the moment. The orbit itself is 224 Earth days. Its rotation period is 243. So it takes longer to rotate around its own axis than anything else. So again, it has a very long day. The day is longer than a year in this case. For Venus, 1 year is 224 Earth days, but for its day is 243 Earth days. So 1 day is longer than 1 year. So that is quite a interesting little planet there. It is also a terrestrial planet. That means it has quite a bit of heavy elements. It is similar size to Earth, mass, and proximity to the sun. So a lot sometime before people think on Venus, it might have life, but we don't know. It is, at the moment, it has quite a bit of carbon dioxide. 96% of the atmosphere is carbon dioxide, and therefore the greenhouse gas warming effect is very large, and therefore it has a much higher temperature as well as a much higher atmospheric pressure, because carbon dioxide is heavier than oxygen. Oxygen is only 2 oxygen. Carbon dioxide is carbon plus 2 oxygen. So carbon is heavier. It's also heavier than nitrogen. Nitrogen is actually a little bit lighter than oxygen. So that's why when we go to higher altitudes, oxygen level drop down, because heavier gas tend to be closer to the Earth. So for Venus, the atmosphere is much more heavy, and therefore its atmospheric pressure is about 4 times of Earth's. It is also very hot because its day is longer than the year, so it is facing the sun much longer time, and therefore it go up to a much higher temperature, for up to 442 degrees C. Although Mercury is closer, but Venus is actually hotter. And Venus also have volcanic activity. Volcanic activity contribute to the abundance of carbon dioxide gas. We believe that volcanic activities produce both methane and carbon dioxide within the under the crust of the planet. In the case of us, is under the Earth's crust. There are chemical reactions going on, producing carbon dioxide and methane. Okay, this one is outside of us, is further away from Sun than us. Is Mars. Mars is the fourth planet. We are the third. It's the second smallest. It has quite a bit of iron, so it looks red because of iron oxide, and that means it has oxygen as well. The iron there is oxidized. That is quite interesting because we know that the oxidation of Earth happens much later, but it seems that Mars has already completed its oxidation much earlier. So some people argue, maybe when the beginning of the solar system, there might be life on Mars as well. So initially the candidates for looking for life outside of Earth is Mars and Venus, because they look similar to us. It has a thin atmosphere. It also have all these craters and so forth created by collisions of something else. Days and seasons are quite comparable to Earth. It has a rotational axis tilted, so similar to us. That means it has seasons. And it has one large hole, probably due to, must be the volcano. And so there are different features there. So there is a basin in the northern hemisphere, covering about 40% of the planet itself. So it must be come from a very large impact. It has 2 moons, quite small and irregular. Okay, outside that we have the giants. The giant is just starting from the fifth and so on. They are huge, and their composition is quite different from the composition of the 4 inner planets. The middle is the Sun, and then we have Jupiter, Saturn, Uranus, and Neptune. Plato is not considered a planet anymore. It was considered a planet, but nowadays they don't consider Plato as a planet. They call Plato a proto-planet, something like that, but instead of being called planet. Okay, the first one is Jupiter. Jupiter is the 5th from the Sun, and is the largest in the whole solar system. It is a gas giant and have a mass about 1,000th of that of the Sun. It is much, much heavier than us. And because of that, it has its own internal mechanisms. Yes, it's mainly composed of hydrogen. Because it's so massive, so we believe it must also have quite a bit of helium. Because helium is heavier than hydrogen, therefore helium will be the core. So in terms of its structure, let me look at its structure. Oh, I don't have its structure, but I do have the structure of Saturn a little bit later on. Jupiter have 79 long moons. Again, that means because it's heavy, it's collected quite a bit of debris, and this debris collide into it, and then some of them form moons. The next one is Saturn. The 6th one, it has a very large ring. The ring is small fragments of meteorites, etc. Again, it is a gas giant with many hydrogen, etc. It has 1/8 the average density of Earth, so it's much lighter than us in terms of density. But because it's so much larger, it's actually heavier than us by 55 times. The interior might have some iron, nickel, and rock, and the core is surrounded by a metallic helium, a hydrogen. Now, we commonly know hydrogen as a gas, but and when hydrogen is cold enough, it can liquefy, and we can have liquid hydrogen. When it is still cold enough and with sufficient pressure, then hydrogen becomes a solid. The hydrogen solid is hydrogen metal. So just beyond that, there will be a metallic layer of hydrogen solids, and then above that we'll have a layer of liquid hydrogen, and then liquid hydrogen together with liquid helium, and finally is the gas outer region. The yellow fuel believed to be ammonia, so there will be ammonia in the atmosphere. There must be some kind of electric current flowing through or charge, and therefore it has a magnetic field as well. The magnetic field is much larger than Earth, 580 times larger, mostly because of its size. So the cross-section of Saturn, that will be similar to the cross-section of Jupiter. The inner core is the heavy rocky things, the helium, etc., and then come with the red region. What's the red region? I think the red region is the other rocky things, etc. And then the pink region is the hydrogen metal, and then after that we have hydrogen, helium, etc., all surrounding it. And the rain itself is mostly derbies. Not much thing interesting here. And the day Saturn has determined to be based on study of the rain. Okay, so its rotation, etc. is rain system, which is mostly ice and a little bit of other things. It's because all the heavier rocks, etc., has already been attracted towards the inner planets. Uranus, 7th largest. Not much feature on it. Both have bulk chemical compositions which differ from that of the other larger gas. For this reason, scientists often classify Uranus and Neptune as ice giants, because they mostly make up of water rather than hydrogen and helium. I found this very, very interesting. Why the heavier water existed outside of the gas giants, why there are gas in the middle of our range of planets. I don't know the answer to that question, but I find this question quite interesting. I probably will research about it and talk about it in my next iteration of Big History. It is the coldest, with a minimum temperature of minus 224 degrees, has a very complex layered cloud structure with water thought to make up of the lowest cloud and methane the upper layers. The interior is mostly ice and rocks. It also has a rain system, a magnetic field, and many, many moons. one interesting about is rotational axis is tilted almost sideways, and therefore is night and day. You are on one pole, then your light and that means no matter how many light can say your sun your 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 time towards the sun took about half a year, although your day is shorter because of your own rotation. But being so far away from sun, the effect of sun to it is minor. It shouldn't see the sun as bright as us. It will be much dimmer. Finally, Neptune is the furthest known planet. Previously, there was Plato outside that, but again, Plato was not considered a planet anymore. It is the first most massive planet. The mass is about 70 times of Earth, slightly more massive than is Uranus. Again, interestingly, it is a little bit denser and physically smaller than Uranus because its greater mass causes more gravitational compression. So it's the gravitational compression causing it to be much smaller. Neptune orbits the Sun once every 164.8 Earth years, and it is average distance of 30 times of our distance from Sun, so it's quite far away. Atmosphere, hydrogen, helium, probably with hydrocarbons like carbon dioxide, and maybe nitrogen. Nitrogen to me is also a very strange element. I don't know why so much nitrogen in our atmosphere. It seems to be quite not playing much of the chemical reactions. It might have a more amount of ice, such as water, ammonia, and methane. Both of them will become solid. However, similar to Uranus, its interior is mostly ice and rocks. There are several mechanisms of heat coming from inside of these giant planets because they are so heavy. Most of them is very heavy, and therefore, as the gas is being attracted towards the center by gravity, it actually heat up. So the center of them would be much hotter. In that sense, that means somewhere between its center and its outer surface, there will be a layer where the temperature will be something similar to Earth, because the temperature range there will be huge. There will be a layer which will probably be able to support life, but we don't know. So that is another interesting thing we can look at in the future exploration of these things. There is also visible weather patterns. If there's visible weather patterns and being so far away from sun, and therefore these weather patterns must be due to the heat generated inside the planet itself. With heat, that means the gas close to the surface of the heat source will get heat up, and when it's heat up, then it will become lighter, and lighter it will move up through the atmosphere, and therefore starting to cause all these weather patterns. It also have a very small faint rain. They have been only visited once by Voyager 2, so we don't know much about them. The NASA has sent orbiter trying to escape the solar system. I think so far there are only 2 orbiters that have left the solar system. And on their way out, they will try to swing the orbiter around the known planets in order to take a look. So these are the last 2 planets has only been visited once by Voyager 2. Voyager 1 seems to have missed them. Okay, so that's for my presentation. Okay, any comments? I better unmute all. Okay. Any comments?
Just very interesting, Albert.
Thank
I
you.
can see how it all comes together, and you wonder sometimes, daydreaming, how long will we be here on this earth? And you're giving us some general timeline there.
Yeah, I think
it'll see us out and our future generations for quite a long while. So that's an unknown, and man wonders. And there's a partial answer there in the bigger time frames.
Yeah, I think that
that's how slowly come together. How they started off with 1 or 2 elements, and the others come in the way you explained it. And here's more of it, and the rotations and the various temperatures on other ones that are further away. Yeah, it's a good understanding of what happens generally. And
I think that the whole concept of big history is like that, is to give a general idea of where we come from, how we get here today, and then by looking at that, we probably can think a bit long term in terms of future.
Yes. And what amazes me is the scientists who have been able to measure all this. So from planets a long way away that we could never get to, we can look at them with various instruments and come up with these constant answers, comparing one to the other and working out the similarities and the differences. So it's quite amazing stuff.
I think it's amazing how much information we can get just from light. As you said, well, except for our planets, we do have sent our spacecraft trying to approach them, but still, the spacecraft approaching them is only taking pictures and then sending the picture back. I think we have collided 1 or 2 spacecraft into one of those planets. I can't remember which one. We have tried to send one down there and then let it descend into its atmosphere, and then before it is destroyed by the atmosphere, try to send us as much information as possible. I think we have done at least once like that, but that would be very interesting. And then the other interesting is how much knowledge we have gathered in the last 300 years.
And I think of the poor people like Galileo who came up with hypotheses, and people like him got persecuted because it didn't fit in with the beliefs of the time, the religious people. It was like a contradiction to what they were preaching. So they were very unfair times.
Well, we are also in a very unfair time at the moment, but it's a different kind of unfair. Today here, we I think the unfairness here today, if I might look at the problems of this virus in America, is very saddening.
Yes.
They have over 1 million confirmed cases, and has almost 70,000 people lost their lives already.
Yes. To me, that country that should have been on top of things and would be way ahead of the rest of the world with all their advancement, were poor performers.
Yeah.
They just didn't know how to bounce the ball and how to react.
Well, I think it's the leadership problem, I suppose.
Yeah.
If their leader has taken, well, we are lucky this time, isn't it? We have a quite good prime minister.
Yes. He was a bit slow, but then he picked up the ball and he bounced it right.
Yeah. When he picked up the ball, we got lucky.
Yes. Yes. No, we feel I think in a good, anyone I talk to, we're in a good situation.
Yeah.
Feel pretty confident that most of us will be okay.
Yeah. And then especially when our economy is more resource oriented. So when the world's economy pick up again, we will pick up. But at the meantime, we should have sufficient food for ourselves, so we shouldn't starve.
Yeah, we won't starve.
We won't starve, so that's the lucky part.
Especially with the wet year.
Yeah, this year is quite wet, I suppose. Okay. Well, why suddenly two of you join in? You join into the wrong forum. I'm supposed to close this one and start the channel today.
Yeah. All right, I'll pull out and see you in 10 minutes. I'll go and get something to eat.
Okay, let's pull out and then we'll meet you on
session.
channel today.
Yes, we'll.
Okay.
Certainly.
Okay.
Bye, Albert.
Bye. Bye.
Are we going to continue the same this one? Or
Okay, we'll see you in 10 minutes.
same 10?